Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guests are from Samplify Systems. We have Al Wegener and Allan Evans. And guys, why don't we just launch into it? I'm curious to learn more about the APAX Acceleration for multi-core applications.
So let's jump in. What we're getting ready to introduce is some new technology from Samplify called APAX, which stands for Application Acceleration Technology. And this applies to any application running on a multi-core CPU whose performance is limited by memory or I/O or storage throughput. And what we do is we accelerate applications which operate on integer or floating point data sets. And, as you know, we got our start in this about a year ago in the high-performance computing market. Schlumberger, the oil and gas exploration giant, is an investor in Samplify, and we've been tuning our algorithm as a result of that. But it also works on a variety of other applications relevant to both visual computing and as well consumer electronics and mobile devices. It supports, it applies to graphics rendering because it accelerates the transfer of textures and wireframe meshes, which are triplet integer and floating point data sets. And it also applies to image and video processing within consumer electronics devices. As a technology, it scales up to, complete data centers. As you know, these top 500 supercomputing sites have hundreds of thousands of cores in them. So we scale up to support, the distribution of high-performance computing applications and their accompanying data sets and intermediate results, across these kinds of, tens, hundreds of thousands of computing nodes. But it also scales down to a single multi-core application processor, which exhibits all the same memory and I/O bottlenecks that we see in HPC applications. So for Samplify, this gives us really an entree into not just the computing market, but also consumer electronics and mobile device market. For Samplify, this will be a pure IP business model. We deliver the technology as both software for Intel CPUs, NVIDIA GPUs, and also as RTL for integration into SoCs and application processors. And technology, we've spent really much of the last year validating the technology with Schlumberger and also Mamiya, both of whom are investors in the company. So, to set up the problem statement here, with multi-core processors, they really reap the benefit of Moore's law, on each successive processing node. As we go from 65 to 40 to 28 nanometer, we basically get a doubling of the number of transistors that you can put on the same size die, and hence, a doubling of the number of cores and a doubling of the performance. However, the memory bandwidth and the I/O bandwidth don't necessarily double for free at each of these processing nodes. Memory interfaces are really mixed signal semiconductor technologies. The speed doesn't necessarily increase for free at each step. And the memory width is really limited by how many pins you can put on a package. When you look at a NVIDIA Fermi GPU, it has 6 memory ports of 64 bits each. That's 384-bit wide memory, effectively. and that memory interface uses LVDS technology, so there's 2 pins for every bit. So that's 768 pins on the device minimum just to support memory. You can't really, what are you going to do? Can you double the number of pins? You're already at 0.5 millimeter spacings on these advanced BGA packages. No, you really can't. And similarly, the host interface, PCI, we go from PCI to PCI Express to PCIe Gen 2, and now finally Gen 3. Looking at this chart, NVIDIA made the jump to PCIe Gen 2 back at the end of 2007. Here we are, 2012, and we're moving to Gen 3. So, the host interface, moves in discrete steps, but, once every 4 to 5 years, not once every 2 years like we know with Moore's Law. So this gap between the performance created by Moore's Law and the memory bandwidth and I/O bandwidth that are limited by other factors creates this gap that's ever growing, and as a result, as these GPUs are being positioned at general purpose computing applications, the ability to utilize all those cores, is quite limited. So these applications tend to run at only about 10% utilization of the GPU compute resources. So, another solution really needs to be found to close this gap. And, we feel our acceleration technology does that. And the technology can really be deployed in a wide, a large number of places within a computing system. It can run as software on the CPU to accelerate memory-bound and I/O-bound applications. It can run in the GPU, either as software or as an IP core. In the GPU, it represents now a single technology that can accelerate both graphics, for graphics data and 3D rendering, both meshes and textures. While DirectX 11 and OpenGL have a variety of texture compression techniques built in, they really don't do anything for the wireframe models. Those are limited to, 16-bit half floats. It can be embedded in the memory controller. It can be put in the south bridge to accelerate I/O, put in the storage controller to improve storage throughput, and put in the network interface or other on-chip peripherals to accelerate interprocessor communications. So we really see a target-rich environment within the computing market of potential partners and customers and licensees. So to further illustrate the problem with supercomputing, this is actually from a white paper from NASA of a application, one of the workhorse applications running on their Pleiades supercomputer, which is one of the top 10 supercomputers in the world. This application overflow is doing weather forecasting. And as you can see from the graph at the top, the sustained performance of this application is only about 2.5% relative to, the peak performance, by, some kind of LINPACK benchmark. So this means that, obviously if you're forecasting the weather, you need to get your results in a timely manner. It doesn't do any good to make all your measurements today and get the weather forecast a week from now. So basically, NASA had to overspecify the hardware on this supercomputer by about 40 times in order to get the turnaround time on the forecast, the weather forecast, in a time that's meaningful. so you can actually.
Rich, I have a question. This is Al. Allan, sorry for interrupting. Can you verify, or you have any anecdotal evidence of this trend that supercomputers are significantly underutilized in terms of their peak capacity?
That's not a new development by any stretch. So, I've seen some studies.
What's the traditional explanation for that?
Well, it comes down to Amdahl's law sometimes, and these. I mean, the enterprise does it as well, right? They over provision just in case they get a spike, right? So I don't know. I haven't read anything recently about this, but with the GPUs, I think it's going to increase, right? Because if you look at some of these systems coming up, like Titan and the Blue Waters, 20 petaflops of potential performance, and I just got to wonder where most codes are really going to be running for something of that capacity.
Okay, we suspect that I/O is part of the problem, that it's just taking too long to synchronize the I/O movements, and I/O is starting to become a bottleneck as we're trying to make that case that NVIDIA graphics chips are still running 16 lanes of PCIe Gen 2, and they've had that since 2006.
Yeah, and it's all going to depend on the application profile, right? I mean, how they're accessing I/O, and it's going to vary quite a bit. So I think you're onto something here.
Good. All right, Allan, back to you.
Yeah, I think one characteristic of high performance computing applications that they all share is that you're taking a single problem, you're dividing it up into millions or billions of bits of elements and distributing that across tens, hundreds, thousands, hundreds of thousands of compute nodes with a corresponding data set that obviously exceeds the memory of any one computing node. So, that's really in contrast to a lot of, more typical data center cloud computing applications where, it might be more transactional based and you are, it's equivalent of, many, many jobs being distributed over many, many compute nodes. When you have all of these compute nodes working on the same problem, and all of these problems are all using the same numerical methods, finite difference analysis or finite element analysis. The only difference is what calculus problem are they solving with it, whether it's computational fluid dynamics or weather forecasting or seismic or, stress for car crash simulations. And these algorithms are iterative. So, all of these compute nodes, they get all the raw data, they crunch on it, and then they have to share with each other all their intermediate results before they can run, another iteration step. So it's very I/O and data intensive to be able to distribute all this, across a large compute array. And as a result, you get the CPUs running at 2.5% average utilization because they're waiting for data. They're waiting for all these intermediate results and data to be distributed across the array. And, another trend is now looking at how do we use the cloud to deploy HPC applications. So you can imagine if all these I/O bottlenecks exist within a data center that's been tuned for supercomputing applications with, 40 gigabit InfiniBand interconnect or 10 gigabit Ethernet interconnect, and tight control of which nodes are crunching on which piece of the data to minimize the distance that everything needs to transfer. You deploy all this on the cloud, you don't know where your compute nodes are going to be. They may not be necessarily in the same rack, in the same bay, or even in the same data center. So, as a result, HPC applications that run on the cloud tend to be even an order of magnitude slower than in supercomputing data centers. So by using our APAX technology, we believe we can actually make it very cost efficient to deploy HPC applications on the cloud, because we can accelerate, really because the I/O is an even bigger bottleneck when you try to run them on the cloud than in a data center. And this now gives anybody. You don't need to have special access to a supercomputing center. You can, anybody can go rent some nodes on Amazon Cloud, EC2, and use it for deployment of an HPC application. So all those same problems that we described for supercomputing, if you shrink all of that down into a single chip, the same problem exists in consumer electronics and mobile devices. All of these application processors, Apple's A5, Snapdragon from Qualcomm, NVIDIA with Tegra 3 now is quad-core. They're all going to multi-core CPUs. And they're integrating a whole bunch of other peripherals, onto the same die. Graphics processors, video codecs, obviously the LCD drivers. All of these are sharing the same 64-bit wide interface to DRAM. And that's really limited by, if I'm a consumer electronics device, one DIMM module versus two DIMM modules is a huge impact to my bill of materials cost. So I want to stick with one DIMM module. And if I'm in a mobile device, the die and the CPU and the DRAM are basically packaged together in a vertically stacked configuration. And those JEDEC standards to do that are really limited to 64-bit wide memory. So you just don't have the liberty of adding a second data port. As a result, all of these peripherals are contending for that memory bandwidth. So as you start running videos, everything uses graphics these days. That all starts starving the CPU for memory bandwidth. So now your quad-core CPU that you spend all this effort building, now performs like a single-core CPU. So by deploying our APAX technology now as a hardware IP block, we can accelerate the memory transfers for each and every one of those peripherals on that die. And now, basically, a dual-core processor, can perform like a quad-core processor because it's not being starved for data by the GPU and the video codec. And you can do this without adding the cost of an extra memory module. And we're actually very excited about, the market opportunity that these represent. I mean, first, looking at the supercomputing market, it's a $12.5 billion market for hardware. If you dissect the data on top500.org, you get 5.3 million cores having been deployed during 2011. So that actually works out to about $2,000 a core. When you consider all the other infrastructure that's required to support, even though a Nehalem CPU may have 6 cores on it, putting it all into racks and bays and cooling and, megawatt power feeds to these data centers, it gets to be very expensive, even on a per core basis. So instead of deploying more cores, accelerate the cores that you already have. predicts 1 billion smart CE devices to be deployed by 2015. ARM's expecting 800 million smartphones in 2014 alone. I think Instat is far underestimating the tablet market in 2014. I think Apple probably surpassed that last year. So it worked out to about a $700 million total available market for our technology, which we're quite excited about. So that's really the quick pitch. If there's anything further you'd like to go into more detail on, we'd be pleased to answer any questions.
Sure. Well, thank you for that. A question about how this is implemented. Is it strictly a software thing, or do you have to put chips on the motherboard to implement the APAX solution?
So it's two ways. The first is it can be deployed as software, and that's how it's been used to date. And the principal way we see it being deployed in supercomputing applications. But we also will be making it available as a hardware IP block that other semiconductor companies will integrate into the various devices within the compute system, whether that's directly on the CPU or in the memory controller or in the Southbridge chip or in the GPU.
So to give you a specific example, and not to say that we've talked with these companies about it, but have you heard of Project Denver at NVIDIA?
Oh, absolutely, yes.
So that'd be an example. I mean, there are other companies. Another one that comes to mind is a company, a startup in Austin called Calzeta, formerly called Smoothstone. And the idea of building server chips that are 10x lower power than today's x86 machines, that's very attractive to anybody that's building enterprise compute farms. So in those cases, they're typically using an ARM processor, maybe the A15, but they get to put their own secret sauce on the rest of the chip. So we're expecting that companies like those will be interested in putting something on there that could potentially make their DDR memories, their InfiniBand links 2 to 4 times faster.
And then what about And what about the overhead in that software only solution? I mean, it takes time, right, to compress data and decompress it.
Yeah, well, so I'll give you a number without saying too much. Let's just say it's on some seismic processing. Mm-hmm. And on actual platforms. We have several flavors of the algorithm. The slow one runs at about 100 megafloats per second, compress and decompress at the same speed, and the fast one runs at 300 megafloats a second. So the performance is slightly different between those, but we're talking about algorithms that are 1 to 2 orders of magnitude faster than today's WinZip lossless compression.
Okay.
And, when the CPUs are only running at 2.5% utilization, there's a lot of spare MIPS to do compression.
Yeah, yeah. So at a highest level, you guys are reducing the amount of bits that are being moved around, and that's what's speeding things up. Is that a fair description?
Correct.
Yep, yep. And I would think there would be some advantages in terms of energy and heat as a result of that, too. Have you looked at that?
Absolutely. Processor for a mobile device. Mm-hmm. The memory, the power consumed in the memory interface is actually almost as much as that at the CPU core itself consumes.
So what exactly are you announcing on Wednesday? Is it just the availability of this and that you're open to partnerships?
It's a technology announcement. The initial form will be as software for HPC applications. Mm-hmm. And we are announcing the availability of it in software form on Wednesday. The IP form for implementation in an application processor by a semiconductor company customer, that'll be later this year.
So what's the call to action, guys? If I'm an HPC user out there with some code, will they be able to download something and kick the tires on this?
Yeah, we support. Our engagement model involves typically working directly with customers to look at their data sets and their the way they store their intermediate results, and doing evaluations on how much acceleration we can get for them. And then, it's basically a software library. They can just compile it in to their existing applications and run it.
And Rich, we're also working on an MPI version of this, so that you could replace the MPI send and receive primitives with MPI send compressed and receive uncompressed. That should be interesting to the HPC guys, because they use MPI all over the place.
So what's the next step? Do you foresee HPC vendors like bundling this together, or is it more, do you think, from maybe the ISVs putting this into their code?
You're right. There's actually numerous ways we plan to go to market with this technology. Just as a software library, we can make it available to HPC end users, who are essentially writing their own applications. So people pretty much who are using like a lot of the existing top 500 supercomputing sites, they, a lot of that is custom written code. And so they will just take the software library and compile it in. As we will have a version that is integrated with MPI, and now that's something where the HPC OEMs, who typically bundle MPI software or middleware with their hardware, can deploy, for free. Not with a small license fee to us.
Sure.
But then, that's pretty much becomes available to anybody using, that the hardware in that data center and using their MPI stack. The third way is, yes, working with independent software vendors, the companies that make the software to do car crash simulations that, are used by the automotive companies. Any of these, they can then compile it in and now offer a turbo version of their software, particularly for doing large simulations. It will be made available to, we pretty much see the guys building application processors for consumer electronics and mobile devices, integrating this onto the die of their application processor. And that's a highly competitive market where, any kind of edge that they can get, is extremely valuable.
Especially if it lowers power.
Yeah.
Look, Samsung makes application processors for the Galaxy Tab and Galaxy S smartphones. Samsung also provides foundry services to Apple for Apple's A5 processor. Samsung and Apple use the same, dual-core ARM Cortex A9 on that same process technology. So is there any competitive advantage that either one of them has in terms of process technology or, raw CPU performance? No. So they get their differentiation by the other cores they integrate on that die, and our core can really, give one of them an advantage.
All right, guys. Well, I really like this. In fact, the fact that you have something that isn't just an HPC play, but it has multiple markets down to the consumer level, the mobile devices. That sounds like a good business plan to me.
Yeah, we're very excited about it.
So that was good. Let me hit the stop button here.